Okay, so we're going to focus just on one example today. Everything is going to be about the simplest case, about the Grassmannian NK. Thankfully, this quiver has been on the blackboard enough times in the past couple of weeks. So the corresponding Nakajima quiver variety is T star Grassmannian Kn. And we will not go beyond this example in the next hour at all, although a lot of things can be done in greater generality. The purpose of my talk today is to say at least something about quantum K-theory of this, or enumerative K-theory. So quantum but don't run away yet. It's not going to get there for some time. So as already in today's lecture, it was already mentioned that, of course, we have to consider the union of all these by k, from k equals 0 to n, of the T star Grassmannian Kn. And then we're going to consider the equivariant K-theory of this. Now, what's the torus acting in this case? Torus is C star A1 times C star A2, etc., C star AN. This comes from the action on W. And then there's an extra toric parameter, H bar, of course, that scales the cotangent fibers, so the T star part. And let's even though this was already said today, I like to do this again. So this will be identified with this is identified with the representation of the quantum affine algebra U H bar SL2, and the representation here is going to be C squared of A1 tensor with C squared of A2, etc., tensored with C squared of AN. All right, and this is not a coincidence. These they actually correspond to the same things, equivariant parameters here and evaluation parameters over here. But the very first thing I want to say that let's just count the dimensions of this. I think that's a good start. So the dimensions of equivariant K-theory for variety is just the number of fixed points. And the number of fixed points, so fixed points in T star Grassmannian Kn correspond to K subsets in an N set. In particular, there's exactly n choose k of them. And I'll write this formula low enough so that it doesn't go to the whole audience, that the sum of n choose k is equal to 2 to the n. If you sum from k equals 0 to n, which is good. 2 to the n, 2 to the n. That's good. And but let's talk about a bit more about this, because we want to identify some very specific objects here in terms of the equivariant quantum K-theory or enumerative K-theory. There might be a copyright on the word quantum in this case, and it's being discussed if we can use that word. So I'll be careful with it. But let's specify some, let's choose some specific operators that we want acting on this space. All right, so in particular, we're going to need the transfer matrix. And for that, we're going to need an extra representation. So that extra representation is going to be also another c squared. So we're going to have c squared of a1 tensor product with c squared of an tensor with c squared x. All this has been on the board today. And we're going to take the R matrix that switches this and this. So here we get c squared of x. Here we get c squared of a1, c squared of an. So this R matrix, however, it's bigger. It's not an operator on the space, not yet, at least. So let me grab my cheat sheet for the future. So first of all, so the transfer matrix is a partial trace of this. So T of x is the trace over c squared of x of the R matrix. The identity also tensor with z. This is just the z is just a weight parameter for the trace, and it will be identified with a quantum parameter. So this this becomes this is an operator on the space. I should call this something. What's a good name for a big vector space like this one? Let's call it X. It's a bad name because the quiver variety is usually X, but Z is just an extra parameter for the trace. It's just a weight of the trace. So now this is an operator that acts on X. This is little x. The little x is this one, and this is the capital X. Okay, and this, since this school has the word physics in it, it's I have to say that all this came from the study of the XXZ spin chain, and that's where this is important. And in particular there, what's important is the Baxter operator. So if you want to understand something, so if you have an operator, you can look at the whole algebra that commutes with it, right? And if you have, and that algebra is called the, I think it's been called the Baxter operator, the Baxter algebra here, but also the Bethe algebra. It's the same. I'm not sure who was first, Baxter or Bethe. Well, yeah, okay, we don't care. So, and for that algebra, you might want to have a better way of understanding it. Specifically, you want to understand a spectrum, and a spectrum is described by Bethe equations. Bethe equations can be, in this case, will be written in the following form. Let me write them down here so they just stay here for the rest of the lecture. So, so Bethe equations from j equals 1 to n, si minus aj minus h bar aj minus si equals z times j product from j equals 1, j not equal to I, si h bar minus sj divided by si minus sj h bar. And I just varies from 1 to k. So this is a system of equations on k variables, si's, and it has some solutions, and symmetric functions of these solutions will generate the Bethe algebra. So in particular, what's a good way to write down the generator then? It's the Q operator, which will be product of from I equals 1 to k of 1 minus si x. So here x comes in just as a generating parameter for symmetric functions, nothing else, nothing fancy like over there. However, turns out that there's a very good relation between this t and this x, called the t and q, called the TQ relation. So the TQ relation, it's the following thing. T of x times q of x equals the product from I equals 1 to n, 1 minus ai x h bar inverse times q of h bar x plus z times the product of I equals 1 to n, 1 minus ai x times q of h bar inverse x. Okay, so this is just a relation between the operator that is a good generator of the Bethe algebra and the operator that we were actually originally interested in. What's interesting about this? Well, first of all, t is polynomial in x, which has been a theme that's been coming up in lectures this week, stuff being polynomial. And this has to do with it, although I don't really understand. What? T. In x. Are you sure that I didn't confuse the variables? In what is it a polynomial? So if you plug in, I might have to change variables a little bit for this to be exactly true, but if you plug in, it becomes equivalent to Bethe equations, pole cancellations over here. The eigenvalues are polynomials in x. Yeah, the eigenvalues are the eigenvalue. Yeah, this is only true. Since this is about the spectrum, this is about eigenvalues, and yes, thank you. So t has eigenvalues of t are polynomials in x, and that is in fact equivalent to the Bethe equations. And you can check that by pole cancellation over here. If you just plug in one eigenvalue, and if you do that, you can probably find some mistakes that I did in this formulas. But you'll see how to fix them. There's probably an h bar here or there or something like that. Okay, and it's just the R matrix for this extra representation. Yeah, as defined this morning. Yeah. With that extra z parameter. Just the identity. Yeah. Okay, so this will be it for. We're going to move to more about the Grassmannian rather than the representation theory. So if you have more questions. Yeah, that was this morning. Yeah. I mean, like the whole purpose of the morning lecture was to construct the action on exactly this space. Well, it's the analog of the Yangian for the K theory. That's the quantum, yeah. But also this morning it was about K-theory, not about cohomology as well. So now it's time to move on to more complicated matter that is quantum K-theory. Let me check the time. Okay. So what's happening next? Quantum K-theory. To do that, I think parts of what I'm going to say were originally planned to be said tomorrow in the morning lecture, but I'm not exactly sure what's going to happen there. So to construct, like in quantum cohomology, quantum K-theory is about counting curves, although that has not been talked about in the school at all, so I'm going to say some things about it. So imagine you have P1 that just lives separately from all you've been looking at. And this P1, you can map it to your variety. I'm going to start calling the variety X. So in this specific case, it's the T-star Grassmannian Kn. And then you can look at the space of maps from P1 into X. So this space, it's very big and pretty ugly. What do we know about it? There's a notion of degree, right? You can still have degree, and it's separated by the degree. So what else? What else just the space of maps has? Also, if you have a point P inside your P1, then you can construct the evaluation map at P from the space of maps into X. Right? And let's imagine, it's not going to be the case at all, that this is a proper map. If it's proper, you can take push forwards. Well, you can take pullbacks, whatever. But if it's proper, you could also take push forwards. So if you have some class on this space, which some K-theory class, we would be able to push it forward. What's a natural class to consider? A natural class, usually if you want to come with big moduli spaces like this one, you would take the fundamental class, but for moduli spaces, you would take the virtual fundamental class. So on this, you have the virtual structure sheaf, because we're in K-theory, not in cohomology. So this lies in K-theory of the space of maps. And note that I took a covariant K-theory because if we have a torus acting on X, we can just lift that action up to the space of maps. So if you have a specific class you're interested in, you can push it forward. So you can take the evaluation push forward at P, sorry, and you will get a class in K-theory of X. You could also take, if you chose 1 point, you can choose 2 points. So you can also take evaluation at 2 points. Take the same class. And this will be an element in the tensor square of X, of the K-theory of X. And from an element in the tensor square using a bilinear form, we can construct, of course, an operator acting on X. So a thing like this, so something like this, gives an operator on K-theory of X. And OK, well, we took the whole space of maps, and the degree can be whatever. it's better to have a generating function. So it's better to actually write down something like this, like a sum over d, which is just degree, z to the d times evaluation at p1, p2, and going from maps of degree d. What?
We have a pass from P1 to this target.
Yeah.
Are we covariantizing the rotation from P1?
Well, not. Sometimes we do, but not for anything I'm planning to say today. But this, it is a very important part of any computation or any. When it comes down to proving something, you definitely, almost definitely, will have to do it. Just I'm not going to actually prove something today. Yeah.
Is z the same as was it?
Yes, exactly. That z is the same as that z over there. I wanted to be consistent with my notation. So yes, of course, the z will be identified. Any more questions? Yeah.
So I'm not sure about cotangent bundles because they're not compact, but if the target was compact, there would be no degree zero term. Is there a degree zero term?
So the degree, well, there is a degree zero term because you can map to a different point depending on where. All maps will be to a point, but you have many points. And the degree zero term will exactly be, the space will be exactly x. The map will be trivial, and you will have identity. Well,
So okay.
yeah, that's that.
So when I set z to 0, I get that.
Exactly, yes. Well, it depends on what like you exactly started with. What's this class, and you got to be a bit careful. But you do get something classical at the very least. That's yeah, and that's a very good point. That this is a deformation of something classical. Since I didn't define the space, it doesn't really make sense to talk about what it is, because it really depends on it. So this whole spiel here was to show that we need to somehow be able to work with the space of maps. And what I have to say next is it doesn't work out. So many things break down. You need like a proper theory. And one thing, of course, is that this is not compact. That is not too big of an issue because the fixed points are compact, and if you consider torus equivariantly, then you can still do it. And a whole other issue is that maps. I didn't say if there are any conditions on this, but they can break in so many ways, and people have spent many years thinking about this. And for most of the time, Gromov-Witten invariants were the way to think about this. But this is not what we're doing here. We're going to do quasi maps. Is it okay? What should I don't want to erase any of the whiteboards, so I'm just going to stay on the black one. So in quasi maps, they bring some solutions to some things, and they bring some issues with other things. Let me keep this for now. So quasi-maps to T-star Grassmannian of k-planes and dimensional space is the following information. This is a vector bundle V rank k together with a section F, but it's not a section of V. It's a section of M plus M star, where M is Hom from W to V. This is unwrapping. And then W is a trivial of rank N. Right, now this, and this is almost it. F has to satisfy the moment map condition. Let me just write it as mu. Meaning that it's, so let's take a closer look at what this is. This is very similar to the definition of T-star Grassmannian as a Nakajima quiver variety, only now instead of vector spaces, we have vector bundles. Right? And this means that for every point in P1, we defined a point in the Nakajima quiver variety, more or less. Well, first of all, let's check. To become a point in the Nakajima quiver variety, there are two conditions. One, that it has to satisfy the moment map, and we put that condition here. And the other one, that it has to be semi-stable. And we didn't put that condition here. And in fact, it's not here. It's not going to be. The only way it's going to be present is in that F is stable almost everywhere. Yeah. Yes. Oh, yeah. Thank you. That's I never on P1. Yes. Well, it's a quasi map from P1. Since we were I was talking about maps from P1. Yes, but thank you. That's a very important point. So technically, this condition is only used for stable quasi maps, but I don't think unstable quasi maps are used for anything. So I'm just going to embed it into the word quasi map. OK, so now this is much closer to so if you can now consider the moduli space of quasi maps, this is much closer to what we wanted. We wanted the space of maps. We wanted to be able to evaluate it at any point. And we could almost do that, but not everywhere. Right? For a quasi map is stable almost everywhere. Almost everywhere means except for a finite number of points. In that finite number, so if you fix a point on P1, you'll definitely at some point find a quasi map that is not stable at that point. So there is no evaluation map at a point P. So it maps to the stack quotient, but not to the Nakajima quiver variety. And we need the actual maps to Nakajima quiver variety if we want to construct an operator here. Yes, yes. The condition is that we have is that every quasi map maps a generic point. But if you fix a point, you will definitely find a quasi map that doesn't.
So do you need to model out
well, when you don't, yes and no. In the definition of a quasi map, you don't. But you're considering moduli space of this, and so what used to be modging out by the group is embedded into that thing. So they're considered up to isomorphism, these vector bundles V. Yeah, it's a fixed P1. It doesn't, it's parameterized. Yeah. Yeah. They are stable in that sense. Yeah. You can check it. It's a natural thing because if you define your vector bundle almost everywhere, well, whatever. That's you could check it if you want. Okay. So problem. Evaluation maps. And there are two ways to go around this problem. And I'll start using the picture notation for them. One will be depicted like this, and the other one will be depicted like this. This is non-singular. And this is relative. So this way is sort of, it's how kids, I feel like, will do it. Let's ignore it. If let's just not work with the problematic ones. So this we consider a subspace, a subset in the space of quasi-maps, non-singular P. So it's just inside of all quasi-maps. It's an open subset, and sometimes you can do this especially if you add a torus acting over here, which is usually called C star Q. Then the fixed locus with respect to that torus can end up being proper, and you can actually do stuff like this, and you can do computations. But it's harder, and it really starts depending on this Q, because if you send this Q to 1, if you turn off this torus, then everything becomes very singular. This is a way to go around this, and for that you need to construct relative quasi-maps, which I'm not going to define, but let me just briefly say that they are just a bit more information than what we had. They're also a quasi-map from a P1, but then sometimes there might be a chain of P1s attached to it, which Andrei calls an accordion, and with quasi-maps over here that are considered up to scaling of this chain of each separate piece of this P1. And of course, there are gluing conditions. It's sort of complicated, but it's complicated enough for me to not have time to talk about it. And the conditions that we would have here is that they're non-singular at the nodal points and non-singular at the end point. So relative quasi-maps is the better way to go around, and it provides us a way to construct operators that do not depend on anything. In particular, we can construct an operator that looks like this. There's also, you want to multiply by this matrix G, which is called the gluing matrix. I'm not going to describe what exactly it is. So if I give you a picture like this, this means that you have a P1 with two relative conditions, meaning 2 points where you can actually do push forwards. And if you can do push forwards in 2 points, you can get operators. And that's all that we wanted. We wanted to get operators. In particular, you can call some of these operators quantum multiplication by K-theory classes. And quantum K-theory is it's the same vector space with the extra parameter Z. So quantum K-theory, it's also covariant and of X is equal to the, as a vector space, it's the same thing as a covariant K-theory with an extra parameter Z. But the product now is deformed. And the operators of multiplication by classes are constructed in this way. Okay, and in particular, one can construct the Q operator. And at this point, defining the Q operator will be easier than the T operator. Can I erase this? Yes?
Is there easy way to see that right there? You get like 2 points is
Well, it depends on what you put in, right? Remember, so when we had these operators, we took a specific K-theory class on the moduli space. And it really depends on what you put in there. Right? So you push it forward into 2 places, and depending on what you took, you get a different operator. Not sure. Yeah. But, well, also, there's one way I like to think about this. So if we imagine we were in classical K-theory, right? And we had let's say we were multiplying 2 fixed points. The K-theory class of one fixed point by the K-theory class of another fixed point. You're going to have 0. But here, now these 2 fixed points, they might have curves connecting them. They might have quasi-maps that go from one to the other. And you're going to have to count these. So that's a way of understanding how this is non-trivial, at least to me. Yes. I don't know. Maybe we can talk later. if you, yeah.
Question is, if I understand it through physics in terms of vortex moduli space, what's happening for this relative vortex?
Yeah. I mean, that's how this bubbling arises. Yeah. Yes, I'm about to define Q. So you can, there are different ways to define Q, which are all equivalent. Let me quickly say again what they are. So one way, I think you were at Kevin's talk, like half a year ago. But I remember. One way to define it is just basically the operator commuting with T satisfying this relation. That's one of the that's an equivalent definition, and I think he defined it that way. This one, this is a relation. Yeah. Yeah, I mean this is not exactly Q. This is eigenvalues of Q. This is a different way of defining it, which is equivalent. That saying that Q is an operator that commutes with T, whose eigenvalues look like this, where SIs are solutions of the Bethe equations.
each eigenvalue is a product of that?
Yeah. So you, yeah.
Where SIs are solutions of this system?
Yes. No, don't. Ask more if something puzzles you.
So Q in particular is defined like T for any tuple of these UGS Q representatives, is that right? It seems like T here for any A1 through JN?
Well, no, because you would have to write down a relation for T and Q. Like if you take a different T, you would have to write down. This is more of a universal thing because you just take the algebra. They commute, right? So. Sorry, let me say maybe. So this you have the Bethe subalgebra, right? Which is defined by this operator T. And Q is just the natural generator of this subalgebra that is given. If you have a commuted commutative algebra acting on something, you want to find its spectrum. And its spectrum are symmetric functions in Bethe equations. So Q becomes a natural generator. Okay, I want to give the geometric definition. So Q of x is going to be the generating function for the follow. So it's the sum from I equals 0 to k of x to the I times this the wedge, the ith wedge of v, and I do it with a hat, and I draw it like this. So this is an operator. So each of these is a separate operator, and this is the generating function for them. So we need to define what's an operator that looks like this. An operator that looks like this is the following thing. So we take quasi-maps relative at 2 points. We also multiply by that matrix G inverse. But other than these two relative points, we choose another one, P3, which is separate from these two. And in that point, we do not put any condition. We do not say relative. We do not say non-singular. We just, at that point, we can evaluate the vector bundle V, and we can restrict it to P3. And if you have a quasi-map, V is part of its definition. It's a vector bundle. And if you restrict it to a point, you get a vector space. So all this together will be, this is a vector bundle on the space of quasi-maps. And for that vector bundle, we can take wedge powers of it. So we can take the ith wedge power of this thing. And this is now, you can take its K-theory class in the Coherent K-theory of the space of quasi-maps. And now that we have that, we can pair it, of course, with the virtual structure sheaf that I mentioned briefly before. And from that, we can construct an operator like this.
Is that the pullback of the topological bundle, or does that make sense?
There's no evaluation at this point. So not exactly. There is an evaluation to the stack, and in that sense it is. But you have to be careful. You actually you want yeah. Yeah. That's so in that sense it is. But so you could say that it's a pullback from the stack. But then you push it forward to not to the stack, but only to the quiver varieties because we have these conditions. I have time. Okay. All right. So these are the operators. The hat, I just put it there because to make, well, if there wasn't a hat, this would be already a well-defined class in the Coherent K-theory, just the tautological bundle itself. And this, it's not it. It's different. That's why I put a hat on it. Any other questions? No. OK, so this way, we identified the Q operator from enumerative K-theory. Now, what's left is to, well, I didn't prove it in any way, and the way it's proved that this is the Q operator is using Bethe equations. Actually, you just you prove that we construct this operator, we compute its eigenvalues, we show that they are symmetric functions of Bethe equations. So, however, you could also identify the T operator, and for that you'll need a slightly adjusted version of quasi-maps. Any other questions? So T operator, and I have to say here, this is perhaps a work. So these results that I mentioned here are joint with Anton Zeitlin and Andrei Smirnov, and this is a work in progress, so might be wrong, but I'm pretty sure it's not. Well, with Karateev, it's not. It's in greater generality. It's not. It's for all partial flags, and there's also some connections to other quantum integrable systems, like Rujina Schneider. I can't pronounce that. The first name was different. Yes.
Is it really independent of Z?
No, it depends on Z because when we take push forward from quasi maps, we get Z. Yeah.
So I'm just concerned about your factorization there.
This one over here? The SI depend on Z over here. But well, actually, since you asked about the Z goes to 0 limit, this is a good point to bring up now. We can look at all this when Z equals 0, right? We're supposed to get the classical K theory, and if you take Z equals 0, the solutions are just AJs. And eigenvalues of such an operator in classical K theory are symmetric functions in AJs. So things, yeah. So it's good in the limit at the very least. Okay, so for the T operator, we need another type of quasi-map, which is a quasi-map with defect. Name subject to change. What this means is that in the definition, so similar definition, but we take W to not be a vector bundle, but to be a vector bundle plus a structure sheaf point P. So the defect is at P. P is in P1. So you can, in the P1 that you're mapping from, you can choose a point, and you can say at that point, it's not going to be a vector bundle. It's a vector bundle plus a structure sheaf of that point. And what happens is now this sheaf is supposed to be fixed. It's fixed. It's the same for all quasi-maps. This one, however, it varies. And as it varies, it might also pick up that structure sheaf of a point, but it might not. So there are going to be different points in that in the space of quasi-maps. So some of them. So this is sometimes. It's a it's a locus where it happens, and now. This is the first time the x that we had over here is actually going to come in a geometric sense. Because before that, it was just a generating function in it. Here, x is on this structure sheaf of a point. We can have a torus acting, C star x. Right, so here we had the n-dimensional torus, which corresponded to these things. And now we have an extra one acting over here. And so this, I don't want to write out the definition because everything else is basically the same as quasi-maps. You take similar HOMs, you take a section of the same things that we had before. You just have to be always very careful because I mean, HOMs from structure sheaf of a point to a vector bundle don't exist, only the other way, and this brings up all kinds of restrictions. But what is nice is that you can do this defect at one point, and all the other points will not know about it at all. So so I'll denote this defect like this, so we can call it P. at point P, multiply it by G inverse as we always did, and we still get an operator. And that operator is going to be T. And the way that is proved is, well, it's a slightly adjusted version of T with like up to some factor that you get T. And the way that's proved is just by the fact that it satisfies this relation with Q. So I think I want to finish very soon. The last thing I want to say, that relation is satisfied. Well, it's satisfied. It's satisfied in a slightly different sense, right? Because it's satisfied for the. Sorry, what did I want to say? So you have to take the non-singular locus, and you can count the vertex, and it's satisfied for the bare vertex actually, rather than the capped vertex. Well, if it's satisfied by the bare vertex, it's also satisfied by the capped vertex. But it's just it's. Yeah. Yeah. I mean, well, it's going to be it's going to be proved in localization on. So when you localize an x, you're going to pick two different components. Yes. That's true. But it's sort of what I wanted to say that this formula doesn't depend on Q, the Q the toric parameter that acts on P1. But you can, the bare vertices, they depend on Q, and they actually contain somehow more information, and the relation is satisfied for them. Okay, but you can also do it just Yeah. So yeah, one last thing before I finish is that this. Somehow this should resonate with what's happening here, because if you think about it, when we're saying that at this one point we're actually considering maps to a greater Grassmannian of points in the n+1, Grassmannian of k or k+1 planes in the n+1 dimensional space, which should correspond to this representation. So there's this is how it's related. This is where it actually comes in some way. And I'll finish here. Yeah, so the geometric part thinks about Grassmannians separately, absolutely. But the representation theory part doesn't, right? Because here we need the disjoint union of all of them. It's just these operators, they act on them separately, the Bethe algebra. Yes. It's just the torus action. So if you have a structure sheaf of a point, you can act on it on the fiber. Yeah, yeah. The SLN I'm currently working through. There's more terms in the relation. So there's a very natural way to construct T in that you can it will look very similar to what we have here. But the relation, I think the way, well, people don't really write out these relations too often, and you can do it in different ways. And I'm not exactly, I think I might have to adjust, just work out. Yeah, there's a bunch of Q operators. Yes, yes. So there's a lot you can do, but I believe it should be generalizable to SLN because the geometric definition of the T operator is just given to you immediately. Yeah.
You're talking about plagiarizing stuff more.
Yeah. You can take a different quiver, which is which is going to give you all partial flags, not just Grassmannians, and you'll have SLN action, and there's still the transfer matrix, and there's still there's more Baxter. There's the Baxter operators are now separate per each vertex. So you have a different tautological bundle, and you have a different Baxter operator. Right.